Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, we'll continue talking about naive Bayes. I think this is where we stopped last time. We were talking about naive Bayes assumption. So what is naive Bayes assumption? We have this conditional probability. If we use the chain rule, then we will get this, which is the probability of the class label times the probability of every feature given the class and the previous features. So this is a very long expression if we have many features. But with the conditional independence assumption that we discussed last time, we can simplify it to this one, which is just the probability of the class, which is the same like here, times the probability of each feature given only the class label. Okay, so that means that no feature depends on the other features given the class label, and that's the naive assumption that we discussed last time. Okay, so this is where we stopped. Now we can start modeling. We can start substituting these probability distributions by specific probability functions. So if we assume that the classes, the label is binary, and also the features are binary, okay, and that's of course just for example, then we can model every probability function as a Bernoulli distribution. So from the previous slide here, we will just substitute every probability with the Bernoulli distribution, Bernoulli likelihood probability, which is the one that I think you saw last time. Right. Now, in order to be able to compute the probabilities or to estimate the probabilities, we will use maximum likelihood estimate that we discussed also last time. Okay, so what was the idea of maximum likelihood estimate? Do you remember? It was before Ramadan started. Right? Do you remember? What was it? What is the idea of maximum likelihood estimation? No, that's not the maximum likelihood estimation. The maximum value of the probability of the data that we have. So we have observed some data, okay, and this data came from a specific distribution. We don't know the parameters of this distribution, so we will guess that the values of the parameters are the values that maximize the probability of seeing this data. Okay, that was the idea of maximum likelihood estimation. And if we do that here, then it will be an issue of just counting the number of observations that had this class label, counting the number of observations that had this specific feature value. Okay, this is what we have here. It looks maybe a bit complicated, but when you see the example, I think it will be very clear. But basically here, we are just counting the number of times this class label appeared, the number of times this class label appeared with this value of the feature, okay, and so on for all features. So let's jump into an example to understand it much better, inshallah. So here's the example that we, I think we introduced last time. Here the problem is that we want to estimate the credit quality of the person given his or her 4 features: the personal status, the job, the housing, and the savings status. So what will we do? The first thing we need to do is to model each feature. Model the class, the class label. When we say model the class label, I mean that we need to pick a probability distribution that will model that feature or that class. So here we have binary class. It's a binary classification problem. We have 2 classes, so it is natural to model the class label as Bernoulli, okay, because we have just 2 outcomes. For the others, we'll see more than 2, and we saw an example last time of when we have more than 2 outcomes. It was the die that has 6 faces, right? If you remember, I think on Thursday we had this, right? We had this, you were not here, right? You here? Okay. So we had this example last time, right? The die with 6 faces, and we were giving it as an example of having multiple possible outcomes, more than 2. This probability distribution that we can use here will be a discrete distribution. So if you look at the features, you will see that I think all of them have more than 2 possible values, right? For example, the personal status, we have male single, we have female, divorced. It seems like 2 values only. Do you see any more? I think, yes, we have male, married also, so we have more than 2 values actually. The job, I think, similarly. House, we have own, for free, rent. Saving status, we have not known, less than 100, and greater than 100. So we have more than 2 for each feature, so we can actually model each feature using the discrete distribution type. What is the implication of that? Here we are saying that we need to pick a specific model for each feature, and that will be like an inductive bias that we add to the classifier based on our knowledge of each feature. Okay? So this is injecting our own knowledge about the features into the classifier by modeling each feature in a specific way. Right. Now let's talk about naive Bayes classifier. How we will actually train a classifier using the knowledge that, or the concepts that we studied so far, and how we can predict a label for a new example. Right. When we use a probabilistic classifier, we actually want to compute probabilities for each class. So we are given an example. Let's say the example is X, and let's say that we have 2 classes. So Y can be either +1 or -1. So what we will do in any probabilistic model, any probabilistic classifier, is to compute the probability for each class given X. So probability that Y equals +1, given that example that we want to predict the label for, and also the probability of Y equals -1, given that example. If we have more than 2 classes, then we have to compute more than 2 probabilities. So there will be 1 probability for each possible class. Okay? Is that clear? Right. Now, let's assume that we computed these probabilities. What will be the predicted class? Yeah, let's say, for example, these are probabilities, right? So we can say, for example, this is 0.7, and this is 0.3. So what should be the predicted label in this case? +1. Why? Because it has the highest probability, right? So that's the strategy here. In any probabilistic model, by the way, in any probabilistic classifier, we will compute the probability for every class given the example. What is the probability that this example belongs to that class? Okay, and if we can compute it for every class, then at the end we will predict the one that has the highest probability. Okay, so that's the idea here. So this is exactly what we see here. Argmax means we will maximize, we'll get argmax over Y, which means that we will return the value of Y, the class, the specific class, that will maximize this probability. Okay? Are you with me? Any questions so far? Now, how we will compute this? This is a conditional probability, right? So what should we use when we have a conditional probability? Which concept we use when we deal with conditional probabilities? Bayes rule. So we use Bayes rule to expand it to probability of Y times probability of X given Y divided by probability of X. Okay, so nothing new here. Okay, type. Now we said that we will compute this for every possible value of Y, which is Y small here, right? Type. For every possible value of Y small, we will divide by this specific factor, which is probability of X. Okay, so if we compute that for every class, every time we will divide by probability of X. Whatever the value of probability of X is, will that change the value of the maximum I mean the class that will give us the maximum value. We are just dividing by a constant. Yani, let's say probability of x, whatever the way that we can get it, is 0.2. So for every probability that we had here, we'll just divide by 0.2. Whichever is highest will stay highest even if we didn't divide by that value, right? Right? So the idea here is that we just ignore probability of x because it will not change the predicted label. Yes, this expression is not, of course, equal to that expression. But why should we care? We care about the predicted label at the end. Okay, the predicted label will not change if we divide all the values by the same value. Okay, it's like dividing or multiplying by constant. So multiplying by constant or dividing by constant will not change the order of the value. If we sort them, they will stay the same. Okay, so if I have two numbers like that, 0.03 and 0.001, if I divide it by 0.7 both, that will not change the fact that the first one is highest. Okay, whether we divide it by 0.7 or not, still the first one will be the highest. And that's what we care in prediction. We care about the predicted label. Okay, so this is like an approximation to that, but of course these are not the same. They are not the same value, of course, but the argmax is the same. Argmax y means the value of y that had the highest value, the highest probability. Okay, so this is an equation. They are equivalent if we add the argmax, but of course the expression itself is not the same. Is that clear to everyone? Type. Now we have this. Now we can apply the conditional independence assumption. Okay, if we didn't apply it, then of course we will have the chain rule, which would be very complicated. But now that we have the conditional independence, we can, of course, this is the feature vector, right? So this is like x1, x2, x3, x4, okay, given y. If we don't have the conditional independence assumption, then we will use the chain rule. But with the conditional independence assumption, this is equal to just the multiplication of every feature given y. Okay, because we said that they are independent, conditionally independent, given the class. Okay, so this is equivalent to this, and that's how we will actually predict. So we need to compute these probabilities. So what are the probabilities that we need to compute? What are the probabilities that we need to compute? It's the probability of every class label and the probability of every feature given every class label. This is actually what we will train. This is the trained model that we will get from the training example. Training examples. We'll see, inshallah, a clear example with that. But that's what we will need to compute. In order to compute these probabilities, we need to get this one. We need to get every possible conditional probability of a feature given the class. No, feature value from the example. We'll see an example. Okay. You will not get a probability for every example, but you will get a probability for every possible feature value. Okay, overall. That will be the trained model. We'll see that. So here we applied both Bayes' rule in the first step and the conditional independence in that step. Okay, so this is why this is called naive, because that's a naive assumption, and Bayes because that's applying Bayes' rule. Okay, naive Bayes classifier. It's one of the easiest and straightforward models. Although it's very simple, it is really good in practice. Any questions so far? Right, let's see how we can actually do naive Bayes classification. So let's get back to the training set that we started with. Now we want to get the trained model. What we will train from that? So what will we do? What should we do? We need to compute all the possible probabilities, probability of the classes, the class labels, and probability of every possible feature value given given every possible class. So first we'll start with, so we are in the training phase now. Okay, so we are given the training set. We need to learn a model or train a model. We are not doing any prediction so far. Right. The first thing is to compute the probability of the class tables. How many class tables we have? We have two only. We have good and we have bad. So we need to estimate the probability of good first. How can we estimate the probability of good? In all, we will use maximum likelihood estimates, which is just depending on counts. So if I told you now, what is the probability of good? You need to count how many times good appeared over all of them. Okay, so how many times good appeared here? Did you count them? Well, just a guess. ما شاء الله يعني ما شاء الله. So 19. Is it 19? 19 خلاص يعني نصدق. طيب, it's 19, yes. Yeah, I know from the other group. I counted with them. So it's 19 over اللي هم ايه بقى؟ لا قولي لنا بقى انت يعني نظرتك ثاقبة ما شاء الله. How many are they? 27. Yes. Okay. Any question about that? طيب, how about bad? The rest, right? 8 over 27. Okay. طيب, these are the easiest ones. And the others are also easy يعني, بس يعني this is maybe a bit easier. طيب, what are the others? For example, all bad the conditional probabilities. For example, probability of own, let's focus on housing now. I need to compute probability of every possible value of housing given every possible value of the class. So how many probabilities for housing we need to compute? How many possible values here? Own, for free, rent. Anything else? 3. And how many classes we have? 2. So for the feature housing, there are 6 probabilities that we need to compute. So the first one, probability of own given bad. طيب, how can we compute probability of own given bad? This is a conditional probability, right? So what should we do? Use Bayes' rule. So Bayes' rule tells us that this is probability of own and bad, which is the joint probability, over probability of bad. So to estimate this, we'll just count. We'll count how many times own and bad appeared over how many times bad appeared. How many times bad appeared? 8. We said it already here, right? Time. How many times own and bad appeared? So where are the bads? This one, this one, this. How many of them are own? This one. Oh, not this one. Oh, this one, yes. Own, bad. And this one, right? And this one. And this one. That's it, right? So it should be 4 over 8. Sorry?
The numerator is missing probability of own.
Did you what?
The numerator is missing probability of own. Isn't that
No. Okay. Probability of A given B is probability of A and B over probability of B, which can be written in a different way as probability of B given A times probability of A over probability of B. Not now. Okay. We'll see that in the prediction, but in training it has to be exact. Okay, with me so far? Type. How about probability of own giving good? Similar, right? Which is probability of own and good, or count of own and good over count of of good. How many are good? 19, as you said. And how many of them are on? Need to count. One, 2, 3, 4, 5, 6, 7, 8, 9, 13. Okay. Any other questions? طيب. Can we do the others? If I told you what's the probability of rent and bad, you know how to do it, right? Rent and giving good, and so on. So you will compute all the conditional probabilities, right? Right. How many of them? You know how to count, right? For every feature, how many possible values times the number of classes. That's for every feature. Okay? If you compute all of these probabilities, this is the trained model. It will be a big table, like this. Okay, very big table. Of course, this is in addition to, so this is the value of the feature, the class, and the conditional probability. Okay, this is in addition to what? What else you need to compute also? Yes, probability of the different class labels. Okay, different classes. So probability yk in general, if we have k classes. Okay, that's the trained model. Yes. Sorry. Why what? Ah, that's the class number k. Okay. Yes. Very good question. What are the model parameters? So this is the model, right? Oh, I told you. You believe me, huh? Okay, that's the trained model. What are the parameters? Any parameters in it? All of these probabilities are the parameters. But that's not just one probability distribution, by the way. And if you sum the probabilities that you will get, they will not sum to one. They are a mix of many probability distributions. Okay? So all of these are parameters that we estimated this way, using maximum likelihood estimate. Okay? And for Bernoulli distribution, there is one parameter. For discrete distribution, there are k parameters depending on the number of outcomes. Okay? And once for class label +1, and once for class label -1. Okay? These are two different distributions, by the way. So all of that is the trained model for the classifier. Type. Did we do any predictions? Any question on that? Is that clear how to do it? Type. Now we can do prediction. Right? We are building a classifier to use it for prediction, right? So if we are given now this example, we have a female single, owns a home, self-employed, and the savings are greater than 1,000. What should be the predicted label? How can we do it? What should we do now? Now we have trained the model, right? Which is in the previous slide. How can we use the trained model to give a prediction here? We mentioned earlier in the lecture that we will have to compute what? Probability of every class given the example, right? So probability that y equals, what are the classes here? Good and bad. So probability of good given A, which is the example here, and probability of bad given A. After we compute these two, what should we do? Yes, the maximum, we will say this is the value of the class that will give us the maximum of them. We'll say this is the prediction. خلاص? طيب. Now the question is how to compute them. How do we compute them? We saw that also in the slide where we use Bayes' rule and the conditional independence. So that will be probability of the class, which is good here, times or multiplied by all the conditional probabilities of the features, of the feature values. So probability of, let's say, AI given good over all possible values of I, all the features. Okay? Type. Do we have this in the table? All of these are in the table. Okay? And similarly, of course, we can compute this. So let's assume that this is what we need from the table actually. It's not an assumption, this is exactly what we need. And this is just part of the trained model. Okay? But that's the part that we actually need for this example. How did we know? Look at the feature values. We need a conditional probability of female single given good and given bad. And we need owns given good and bad. We need self-employed given good and bad. We need savings greater than 1,000 given good and bad. These are the rows from the trained model that we need for this example. Okay? And these, let's say that these are the computed probabilities already. Now, how can we compute, how can we do the prediction? We do the multiplications, right? We do the multiplication. So, can I write it as an expression here? It will be probability of, let's say that I want to compute probability of good given A. It will be probability of good times probability of female single given good times probability of owns or owns given good times probability of self-employed given good times probability of savings greater than 1,000 given good. Right? Here it is. This is the probability of good, 0.7. And what is this? That should be probability of female single given good, right? How did we know that it's 0.28? From the model. Just look up the probabilities from the model. The model is trained offline, of course. Given the training data, we get the trained model, which is just the table of the probabilities. We'll just substitute here. So probability 0.28, that's female single given good. Then owns given good. Where is owns given good? 78, right? Then self-employed given good. Then savings greater than 1,000 given good, which is 0.06. Type. Any question about that? And similarly, we can do the bad class. Type. Now we have these numbers. What should be the prediction? The first one, of course, because it's the highest, right? So in this case, we should predict that since the probability of good given A is greater than bad given A, then we will assign the applicant the label good credit. Type. Now my question is, are these probabilities exact probabilities? Why not? Yeah, because we didn't divide by the probability of the example. If we divide by the probability, the exact probability of the example, this should sum to 1. But now, as you see, they don't sum to 1. Do we care about that? For getting the predicted label, we don't care. We don't care. We care about whether it's good or bad, right? But sometimes actually we care. Sometimes we care about this. Can you guess when should we care about this? About the exact value of the probability? Yani what could be an exact value of the probability? Yani for example, if we actually divide by probability of x, maybe we'll get something like this, 0.73, and what should be the other one?
1 minus 1.
Okay, which is 0.27. Okay? Type, why should we care about getting these numbers? Any guess? Something, by the way, we discussed before in the course. طيب, do you think we can أنا بس عايز أتكلم في النقطة المهمة. Do you think we can give the user these numbers? يعني let's say that the user طبعا the employee of the bank يعني, okay, we are trying to use this our classifier. We told the employee, okay, this applicant has good credit, and we give that score 0.0012. Will that be, will the employee will be happy with that? Will he understand this? But if we give him this 0.73 and we told him that this is a probability, it's between 0 and 1, would that be of importance? What do we call that? A word that we used before in the course. What is this? What is this with respect to the classifier? The confidence. Exactly. The confidence of the classifier. If that number is 0.99, that would be really very confident. The classifier will be really confident, and the user will understand it, right? Okay. But if that 0.51, it will be the same prediction, by the way, because 0.51 is greater than 0.49, right? But of course, with 99 or 90 or 85, the confidence is higher. Okay. So if we care about confidence, we have to normalize these values by computing the exact probabilities.